Good morning, students. Today we are going to discuss about Kirchhoff's voltage law. Here we are going to discuss about the loop rule, how the different loops are performing, and how to calculate the loop currents in there. Kirchhoff's voltage law, on the other hand, states that the sum of the voltage rises and drops around any closed loop in a circuit is equal to 0. In simple terms, it emphasizes energy conservation within a circuit. Mathematically, Kirchhoff's voltage law can be expressed as the potential summation of potential rises is equal to summation of potential drops. Here, V stands for voltage, which is the electric potential difference across a component in the circuit. Rises refer to voltage increases across components like voltage sources, example batteries or generators. These voltage increases are typically positive in the equation. Drops indicate voltage decreases across components like resistors or other loads as you move along the loop. These voltage decreases are usually considered negative in the equation. It can be mathematically expressed as summation of potential rises is equal to summation of potential drop. Here, V stands for voltage, which is the electrical potential difference across a component in the circuit. It is important to note that when encountering a new circuit element, if the sign is positive, it indicates a voltage drop across the element, and the element voltage must be subtracted. Conversely, if the sign is negative, it indicates a voltage rise across the element, and the element voltage must be added. This approach helps in correctly determining the voltage changes across elements in a circuit. To apply KVL, the voltage rises positive contributions and voltage drops negative contributions across these components are considered as we consider for the closed loop. The sum of these voltages must equal for a closed loop. Let us demonstrate Kirchhoff's voltage law with an example circuit. Here we have a simple example circuit with one loop. There is a voltage source V is equal to 20 voltage, that is source of voltage has been represented by Vs. The upper side is positive side of the battery and the lower is negative side of the battery, and three resistance has been connected in series, that is capital R1, R2 and R3. The values has been represented as 15 ohm, 20 ohm and 5 ohm. We can find out the current flowing through the circuit using the series or parallel techniques and Ohm's law. Since the resistors are in series, we can find the total resistance by summing up the individual resistance of the three, that is 5, 20 and 15. Totally it becomes 40 ohms. We can find the current flowing through the circuit through Ohm's law. So we know that P is equal to IR and I is equal to V by R. So the P has been given as 20 and the resistance, total resistance, as now we have calculated 40. So 20 by 40 is equal to 0.5 amps. This is the value of current. We can find the voltage drop or difference across each resistor. So for voltage drop, we have to multiply the resistance value into the current value. Because all the resistance has been connected in series, the same current flows through R1, R2, R3. That is 15 ohm, 20 ohm and 5 ohm. Now we are calculating the drop across resistance R1, R2 and R3. So the values has been calculated as 7.5 voltage, 10 voltage and 2.5 voltage. Let us validate Kirchhoff's voltage law using the result we have obtained from our previous calculations. In this circuit, we have only one loop. As we transfer the loop clockwise, we account for voltage rises from sources and voltage drops across resistor. For voltage source, the voltage has been moved from positive to negative. Applying KVL, the loop we write Vs, then the potential difference is plus to minus, then drop minus VR1, then minus 2, then for VR2 also plus 2 minus, and VR3 also plus 2 minus, and voltage source has been considered minus 2 plus, that has been determined as positive. So after substituting the values, 20 minus 7.5 minus 10 minus 2.5, so we are getting the equation state that the sum of the voltage rise from voltage source minus the voltage drops across resistance R1 onto R3, that is 7.5 10 2.5, putting together it is 20 voltage and source is also 20 voltage, so 20 minus 20 is 0. This equation illustrates the energy balance within the loop, hence validating Kirchhoff's voltage law.